Hello and welcome to Numerical Integration. This lab will focus on the following goals. First, we want to understand why we use numerical methods as opposed to analytic methods. Two, we want to refresh your basic concepts of numerical integration. And three, we want to demonstrate how to program the left sum numerical approximation to an integral. We're going to start off with why should we use numerical integration? So there are three main reasons. The first, there may not exist an antiderivative for a function. So basically, not all functions have antiderivatives. Two specific examples are shown below. For the first problem, Mathematica simply returns the question unanswered. In the second case, Mathematica still generates an output, but is in the form of a special function. So these are two examples of functions who do not have antiderivatives, and thus we would have to use numerical techniques. The next reason is that often we are not given an explicit function, but rather our information is data. As an example, say there is an oil spill. If we had a function that represented the rate at which the oil was spilling, we would be able to integrate it to find the total amount of spilled oil. Of course, in real life, we wouldn't be given such a function, but instead we may be able to check the rate at which the oil is spilling if we take repeated measurements at the point where the oil is spilling. Thus, we could have a list of data representing the rate of change of the oil. And then we could use numerical integration, which would allow us to approximate the total oil spilled. So the third reason for using numerical integration is that analytic solutions can be time-consuming. So below, I've calculated the integral using both analytic, i.e. the integrate command, as well as the numerical and integrate command. Using the command timing, we can see how long each process takes. Note the time difference shown below. Now, while you may not think that 62.5 seconds is that extreme, understand that it may be the case in a more complicated real-life problem that an integral like this may have to be calculated 100,000 times or over 100,000 different intervals. In this case, numerical methods clearly have value. So next we want to review how to find the left sum approximation. Recall that given some function, f of x, to find the left sum approximation of the integral from a to b, for instance, we would first divide or partition our interval into smaller pieces and label the points as follows. So I would divide my region, I would label the points x0, x1, x2, so on and so forth until finally xn. Next, we would form some rectangles. If I look at the first interval, I will draw a rectangle whose height is defined by the value of the function at the left point of each subinterval. So for the first interval, I have a height of the function evaluated at x sub 0, and then a thickness of whatever that interval length is. And I would repeat that process, creating the rest of these rectangles, so on and so forth. So if I look at some arbitrary point in the middle, x sub I, the height at that point would be f of x sub I. The thickness would be delta x, and then the area of just that rectangle would be f of x sub I times delta x. And thus our approximation of the area under the curve from A to B is just the sum of the area of these rectangles. And we can write that as the sum from I equals 0 to n minus 1 of f of x sub I delta x. Note that the sum ends at I equals n minus 1 since the height of the last rectangle is the function evaluated at x n minus 1 and not x sub n. So this is the quick refresh of the left sum approximation. Now of course if we wanted to use 1,000 intervals instead of maybe 6 intervals, we wouldn't want to do these calculations by hand. So instead we want to program Mathematica to do these calculations for us. So now I'm going to create a function to calculate this left sum approximation. Now there are many ways to go about writing a program. What I'm going to detail in this video is how I think about the program and go about creating it. In general, I think it is a good approach, but something different may work better for you. I like to start with a specific, easy example and calculate each piece as I go along. This helps me to identify mistakes early. The example I will use is integrating the function x squared from 1 to 2 using 10 intervals. Thus, for this problem, I've identified my function. My function value is going to be x squared. I'm integrating from a equals 1 to b equals 2, and I'm using n equals 10 intervals. So those are the specifics about my problem. I can evaluate those values. Now to find the left-hand sum approximation, which is equal to the sum from I equals 0 to n minus 1 of f of xi delta x, I would have to find out this delta x and each of these xi's. To find the delta x, I take the length of the interval, which is 2 minus 1, or b minus a, and I divide by the number of intervals, or in my case, I divide by n. And this is going to be my delta x value. When I evaluate that cell, I get a value of 1/10. And if I'm going from 1 to 2 and taking 10 steps, I expect each step to be 1/10. So now that I've confirmed that value, I'm going to end my command with a semicolon and reevaluate to hide the output. Next, I need to make a list of my xi's. To do that, I will use the table command. So I will make a table, and now I have to think about what each of these xi's is. So x0 is going to be my a. I'm starting at the value x equals 1. So x sub naught is 1, or a. Now to find the next value, I would start at a and then add the interval length. So a plus my delta x. And that would represent the next point, x sub 1. X sub 2 would just be starting at a and adding 2 of this interval length. The next value would just be adding 3 of this interval length. So for any specific x sub I could just start at a and add I of that interval length. So to make this list of all these points, I just take a plus I times delta x and use my I values that run from 0 to n. Now that I have my list and I can confirm that those are the right values representing those points from 1 to 2, I'm going to name my list xi so I can call and use this list later. Now if instead of seeing the whole list I just want to see one specific value, well then I just enter in the list name and use braces and the value from the list I want to take out. So in other words, that would be the first value from the list, or maybe the third value from the list. So I can pull out those specific xi's. Next, if I want to evaluate my function x squared, at this point, I just say f of that point. And sure enough, that's that value squared. Now if I take that function value, which represents the height of one of my rectangles, and I times it by delta x, well then that would represent the area of one of my rectangles. Then lastly, if I want to find the left sum approximation, I just need to sum up all of my rectangles. Now notice the x sub 0 is the first term in my list. So there's a difference between the first term, term number 1, and x sub 0. I'm off by 1, which means the very last term in my list would actually be the n plus 1 term. So if I want to sum from I equals 0 to n minus 1, I'm actually using the first 10 or first n values of my list. So I will be summing from I equals 1 to n in this case. But notice that even though I'm summing from I equals 1 to n, really the x sub values I'm using are x sub 0 to x sub n minus 1. So when I evaluate that, this result is the left sum approximation to the integral using my 10 intervals. Now to see if my code is working correctly, I can compare this to the Mathematica's value using n integrate. So I could n integrate my function f of x from 1 to 2. I get a value of 2.33. Now you might look at that and say that's not a very good approximation to what Mathematica came up with, but I can always change the values n to improve this. So if I use n equals 1000 and reevaluate this cell and reevaluate this cell, I'll get an answer that's closer. So now I can see that my approximation is matching up with Mathematica's. Now one of the nice things about Mathematica is that I've constructed these cells in a very natural way. I could actually leave my code like this and just change the values and use it for other problems. For example, If I wanted to find the left sum approximation of the definite integral that was e raised to the x squared from 2 to 5, notice this is an integral that I actually have to do numerically because it doesn't have an antiderivative. I could just change my function value and my values of a and b. So from 2 to 5. And I simply evaluate this cell and evaluate this cell, and I'll get that value. And so this way I can adapt my program to other problems. Now, last thing I want to talk about is function form. So while we could use our code just as is, as I've just described, oftentimes it'll be more useful to wrap this code up into a nice function. To do that, I will choose a function name. So for instance, my function name may be left sum, and I'm going to input my variables. In this case, this is the function that I'm using, the interval values, and the number of intervals. Next, I want to use the module command to protect any other variables that I create inside of my functions, as was described in the previous lab on creating functions and programs. So I'm going to use a module. I'll be able to put my variables into those brackets. And then I simply copy and paste in the code that I had written earlier. So in other words, I copy and paste my previous running code. Now the only two variables that I've created inside of my function are my delta x and my xi values, the name of my interval and the name of my list. So I'm going to put those into the module to protect it. Now I'll evaluate my cell, and I've created this function. To test my function, I can just type in left sum, and maybe I'll define a new function. This function will be g of x is equal to x squared. Now I'll take the left sum of g of x from 0 to 1, and I'll use 10,000 intervals. Notice I get an answer that's very close to 1/3, which is the true result. So that should verify that my function is running correctly. And that concludes this video on numerical integration and the programming of the left sum rule.